Thank you, everyone. Good morning. Today I'm going to be talking about nonlinear input-output analysis, and specifically, we're going to focus on the boundary layer. It's a convectively unstable flow. It has many similarities. The approach we're going to be following today with the previous talks. And I want to mention that this is work that I did while I was at Caltech. I finished it last year. And I would like to thank also Denis for visiting us at Caltech and continuing the collaboration on this project. So, as we said, we're going to be focusing on boundary layer transition. And although the configuration of a boundary layer is very simple, the mechanisms, the underlying mechanisms at play that they cause transition, they're quite complicated, and there are actually quite a few of those. At the moment, we can quantitatively evaluate those mechanisms only by doing expensive DNS. We can get an insight of the fundamental mechanisms causing transition using at the local model instabilities, and these are typically responsible for K and H-type transition that has been observed many years ago and also validated through DNS and experiments. More recently, non-normal growth came into play, and other types of transition were proposed, like oblique waves, as we can see here. And actually quite interesting, as we're going to show, nonlinearity actually kicks in afterwards and gives rise to streaks that actually they break down at the end. What has that to do with us? So in that case, the skin friction overshoots and causes increased drag. So we'd like a predictive model to understand the fundamental mechanisms behind all of those transition mechanisms, but also we would like, most importantly, to understand what is the most important and efficient mechanism to transition in a flat plate boundary layer. So this is the configuration we're going to be looking at today. Super simple, as I said. And we're going to having two types of forcing considering. One is going to be a wall boundary forcing that promotes transition. So this could correspond to a vibrating wall, blowing and suction, or any kind of actuator you can think that is on the wall. In the same time, we can have also volumetric momentum forcing. And we can think of that in two ways. For example, it could be a vibrating ribbon within the flow. But what I would like you to focus today is that we're going to consider volumetric forcing representing environmental disturbances, that they excite the convective instabilities, and finally they cause transition. So this can be free stream disturbances, for example. Regarding the linear mechanisms, especially in this community, I don't want to mention many details. In a linear framework, there are two approaches. Looking for optimal initial conditions in the time domain. So you choose a specific optimization horizon time, and you try to find the most amplified disturbances, combining both model and non-model effects. In the frequency domain, this analysis is known as resolvent analysis. And of course, in both cases, we have completely ignored the nonlinear terms associated with the Navier-Stokes equations. So if we want to predict the transition in a boundary layer, which is predominantly nonlinear, we really have to take into account nonlinearity. And the linear part is typically associated with two main mechanisms, as we mentioned earlier, the streaks and the oblique waves. So this is the result of a linear stability analysis, a linear resolvent analysis specifically. And on the right, we see the associated structures with streaks and oblique waves. So now if we want to go to the nonlinear framework to be able to predict actually all the transition scenario and steps from the Blasius boundary layer to a fully, or at least to a turbulent-like boundary layer, we have to take into account nonlinearity. And the tools from the time domain have been recently extended. There is the annual review from Rigas that discusses all the relevant details associated with that. And on the bottom left, I'm showing two representative snapshots of these solutions. The one on the left is the one calculated from Stefania Cherubini for a flat plate boundary layer, is the minimal seed that causes transition, and on the right-hand side is nonlinear solutions that they live at the edge of chaos from Duguet et al. So as you can see, there are two choices regarding time or frequency domain and linear or nonlinear analysis. And you can see there is a big gap on the bottom right that is missing. And this is where we had the idea to try to push towards this direction and provide a complementary approach to the above studies for studying transition. So how would someone include now nonlinearity in the frequency domain? It's exactly a follow-up and an extension of the previous talks. Someone could start with a quasi-linear approximation. In that case, you can prove or show that it's a harmonic balanced approach by keeping only one frequency. Here we have the top equation is the mean flow equation forced by the nonlinear stresses resulting from the self-interaction of the first harmonic. And of course, if you keep increasing the bifurcation parameter or any kind of control parameter you have, in our case, is going to be the amplitude of the forcing, you need more and more harmonics to converge actually to the true solution you would get from a DNS. So with two harmonics now, you get more nonlinear terms. We see at the mean flow order, you get the self-interaction of the second term. And these nonlinear terms also appear at higher perturbations levels. So this theory, of course, can be generalized, as Yasin also said earlier, in an arbitrary number of harmonics omega. And now, in our case, for the flat boundary layer, we're going to play exactly the same game, but assuming two periodic directions. So we assume periodicity both in omega, in frequency, and the spanwise, which is an invariant direction. And we're going to do the harmonic balance simultaneously in both directions. So a quasi-linear approximation in that case would involve only nonlinear interactions at the first level. And in that case, it could have a streaky mode, which is a steady spanwise varying mode, a planar oscillatory mode, like, for example, a TS wave, let's say, or an oblique wave having components both in frequency and beta. I cannot even write in that slide the model for two harmonics because there are so many terms involved. But in general, we can generalize the harmonic balance method in an arbitrary number of harmonics in beta and omega and take into account all the nonlinear interactions between those. So we have formalized that also numerically. We have built a nice method and a nice package that solves in 3FEM the harmonic balance Navier-Stokes equations for an arbitrary number of harmonics, both in the spanwise now and in the frequency. So we truncated using N harmonics and in frequency and M harmonics in spanwise. The solution of that system, you can imagine, is a bit tricky. It's a large system coupled, and we use actually a Newton method to solve it. So in order to invert a matrix after linearization to get the correction, we had to come up with a quite smart preconditioner combining a GMRS and a block-Jacobi method. So we validated our method by for standard cases for transition. Specifically, we examined K-type transition, and we validated against DNS from Rist and Fazel. So transition in that case is promoted by a specific pre-specified boundary blowing and suction comprising of a steady wave with beta 0 and a TS wave with 0 omega periodicities. On the bottom left, we see the comparison with the DNS, and actually the symbols is the DNS, the lines is the harmonic balance using either 2 or 4 harmonics in each direction. And we can see that we're capturing the main behavior both qualitatively and quantitatively. This includes both saturation, both mean flow deformation, and as was presented in the previous talks, nonlinear energy transfer between different harmonics. For example, in this case, we can see energy nonlinearity actually exciting parametrically the oblique waves through the interaction of the steady and the TS wave, which consequently also goes to higher harmonics. On the right-hand side, we can see that actually we can get a really good prediction of the hairpins that actually appear on top of the low-speed blue streaks. But in the specific study, we're not interested on simulating pre-specified forcing mechanisms. We're interested in finding the worst case mechanism that promotes transition. Instead of having a wall forcing, we're going to assume a generic volumetric forcing. And now we're going to do a nonlinear optimization by building the following Lagrangian. Since the problem is nonlinear, we have to specify a forcing amplitude now. And also we have the ability, instead of using the energy of the perturbations, like in most linear approaches, to use also derivatives of the mean flow. And in that case, we're going to use the wall shear stress, which is the most representative measure in order to understand and to understand the transition mechanism. Instead of constraining the equations with the expensive DNS, we're going to constrain it with a harmonic balance, Navier-Stokes, truncated at a specific order, and we're going to solve this problem with adjoint looping. So these are results by assuming that the forcing acts only on a few harmonic components. Specifically, we're choosing a steady wave, a planar 2D wave, and an oblique wave. And we're asking the following optimization question. What are the components and what is the spatial structure for a pre-specified amplitude that causes transition under this constrained forcing? So we did that for a range of frequencies and spanwise wave numbers. And actually, we find that the most important nonlinear mechanism is the one called C here, is very close to the linear mechanism, and is related with oblique waves and the generation of streaks. Nonlinearity is very important for transferring the energy between harmonics. In that case, we go from the first harmonics to streaks with twice the spanwise wave number. And now we can expand the forcing and we can assume even more harmonics. So in that case, we assume 2 harmonics in frequency and spanwise wave number. And actually the gain map, what is the frequency and wave number of the most dangerous mechanism, more or less coincides with one we found before, but has 10 times higher efficiency for promoting transition. If we look in the resulting structure, we can see that it's a combination of an oblique wave, and a TS wave at twice the frequency, which is the typical, actually, AIDS type transition mechanism shown by Herbert many years ago, actually. Similar scenario follows afterwards. The oblique waves, they send energy to twice the spanwise component, promoting streaks. And if we increase the amplitude of the forcing, actually we can see the transition through the breakdown of the streaks. So this is where the interesting results start coming in. And in the beginning, because we're trying to save computational resources, this is somehow an expensive problem. You need a big workstation to solve it. We're imposing a reflectional symmetry in Z. As I said, by increasing the forcing and also the number of harmonics in our expansion, we need at least 4 harmonics in the spanwise wave number and 2 in frequency to see the transition. And actually, we can see the overshoot of the skin friction coefficient all the way to the turbulent values. We see actually the breakdown of the streaks and the generation of the hairpin vortices that cause the transition. However, because this is a nonlinear problem, we cannot guarantee a unique solution. And in order to see actually if there are any other solutions, we started perturbing the solution with noise. We didn't find anything significant, but when we relaxed the reflectional symmetry assumption, actually we found a symmetry break of the Z symmetric states I showed on the left. And in that case, solutions bifurcated from this reflectional symmetric cases. And now the low-speed streaks, they break down in a sinuous manner with streamwise vortices. Actually, this is seems to be relevant with the self-sustaining process as well. And it seems with this approach, we can capture it. And the self-sustaining process, the quasi-streamwise vortices are a key component for the transition process and the regeneration of the oblique waves, streaks, and this whole process in a loop. How far we can go with that? It seems actually we can go quite far, but the whole harmonic balance seems to break down when we enter the turbulent empirical values of the skin friction. This is where energy bursts in all the higher harmonics. But actually, we can see that for the non-symmetric, the symmetry broken solutions, where we don't have reflectional symmetry, if we plot the velocity profile further downstream, close to the end of the domain, we start recovering actually a logarithmic profile. And here I specifically plot the one that is typically observed for fully developed boundary layers, turbulent boundary layers with a dashed line. And we can see actually that the harmonic balance solutions, they start approaching this slope. With that, I would like to summarize, leave some conclusions here. There is an archive if you need more details about the method or the other conclusions we had. And with that, I would like to take any questions you may have.